We saw in the previous video that the linear map L from R2 to R2 defined as L of x comma y is equal to minus y comma x does not have an eigenvector or eigenvalue. We saw this by observing that L rotates R2 by 90 degrees in the counterclockwise direction. However, there is another way of seeing the same fact. L has an eigenvector if and only if there exists some x comma y such that L of x comma y is equal to lambda times x comma y. But notice that L of x comma y is equal to minus y comma x. In other words, we have to solve the simultaneous system of linear equations. Minus y is equal to lambda times x and x is equal to lambda times y. Therefore, if you substitute the second equation in the first equation, we will get minus y is equal to lambda square times y. And this will hold if and only if either y is equal to 0 or lambda square is equal to minus 1. But if y is equal to 0, then x is also equal to 0 and therefore x comma y is equal to 0 comma 0. And we were looking at a non-zero vector that satisfies this equation. Thus, the only possibility is that lambda square is equal to minus 1. However, we know that there does not exist any such real number. Thus, our linear map L does not have an eigenvector or eigenvalue. This is another way of looking at the same fact. Further notice that the obstruction was to the existence of eigenvalue actually. And therefore from now on we will talk about existence of eigenvalue. Finally, you should also observe that even though there does not exist any such real number, there exists a complex number I, the iota, such that I square is equal to minus 1. Therefore, if we had considered the same function from C2 to C2, then it would have an eigenvalue. More precisely, if you consider the linear map L from C2 to C2, defined as L of x comma y is equal to minus y comma x, then we have the eigenvalues lambda is equal to plus I and minus I. Further, if lambda is equal to I, then x is equal to iy. In other words, x comma y is equal to iy comma y. On the other hand, if lambda is equal to minus I, then x is equal to minus iy, which implies that x comma y is equal to minus iy comma y. Therefore, a choice of y gives you an eigenvector for lambda equal to I and similarly for lambda is equal to minus I. Therefore, vectors of these forms are eigenvectors for the linear map L. Motivated by the previous example, it is natural to ask the following question. If V is a vector space over C and L an operator on V, then does L always have an eigenvalue? And not so surprisingly, the answer to this question is yes. The next goal is to understand why this is the case. Let V be an n-dimensional vector space. Let similarly V be an element in the vector space V. And further, let us denote the map L composed with etc. k times by L power k. Then we can consider the list of vectors v, L of v, etc. up to L power n of v. Notice that this is a list of n plus 1 vectors in an n-dimensional vector space. Therefore, it has to be linearly dependent. That is, there exists constants a0, a1, etc. up to an such that a0 into v plus a1 into L of v plus etc. up to an into L power n of v is equal to 0. But this reminds us of polynomials, and therefore we can rewrite this as a0 into I plus a1 into L plus etc. up to an into L power n acting on v is equal to 0. Now, if we instead consider the polynomial a0 plus a1z plus etc. up to an z power n, then the fundamental theorem of algebra states that it has a root. That is, there exists a complex number lambda such that a0 plus a1 lambda plus etc. up to an lambda power n is equal to 0. Further, it can be observed that if this is true, then we can write the polynomial, let's call it p of z, as p of z is equal to z minus lambda into q of z. Further, notice that degree of q of z is strictly less than degree of p of z. Therefore, by applying induction on the degree of the polynomial, we can show that we can factorize any polynomial p of z. That is, we can express the polynomial a0 plus a1z plus etc. up to an z power n, which we denoted as p of z, as c into z minus lambda 1 into z minus lambda 2 so on up to z minus lambda m. Notice that here we wrote m instead of n. That is because we do not know whether the degree of this polynomial is equal to n or not. It will not be equal to n if an is equal to 0, for instance, and we do not know whether an is 0 or not. And in general, m will be the degree of this polynomial. It is also an easy verification that if a0 plus a1z plus etc. up to an z power n is equal to c into z minus lambda 1 into z minus lambda 2 etc. up to z minus lambda m, then a0 I plus a1l plus etc. up to an l power n is equal to c times l minus lambda 1 I etc. up to l minus lambda m I. Of course, here there is a slight trick. You have to understand what we mean by product of these linear maps. By the product, I mean L minus lambda 1 I composed with L minus lambda 2I and so on up to L minus lambda mi. With this notation, we can verify that a naught I plus a1l plus etc. up to an l power n is equal to c times l minus lambda 1I dot l minus lambda mi. Further, we know that a naught I plus etc. up to a n l power n acting on the vector v gives you the zero vector. In other words, c times l minus lambda 1I etc. up to l minus lambda mi acting on the vector v gives you the zero vector. In other words, the composition of these n maps is not an injective function, which implies that at least one of these functions cannot be injective, which implies L minus lambda I into I is not injective for some I. But then lambda I is an eigenvalue of L. Thus, we have proved that indeed the answer to the question we had asked earlier is yes. Recall that when we considered vector spaces over R, the obstruction to finding a basis with respect to which the matrix of the linear map is a diagonal matrix was that sometimes the linear map did not have eigenvalues. However, we saw that if V is a vector space over C, then any operator on V will have an eigenvalue. Therefore, it is natural to ask the following question. Let V be a finite dimensional vector space over C. Given any operator L from V to V, does there exist a basis of V such that the matrix representation of L with respect to this basis is a diagonal matrix? Unfortunately, the answer to this question is still no. Let us look at an example illustrating this phenomenon. Consider the linear operator on C2 defined as L of x, y is equal to x plus y, y. Let us try to find the eigenvalues and eigenvectors of this linear map. Notice that if we want L of x, y to be equal to lambda times x, y, then we need to satisfy the following two equations. Namely, lambda x is equal to x plus y and lambda y is equal to y. The two equations are equivalent to lambda minus 1 into x is equal to y and lambda minus 1 into y is equal to 0. Now, lambda minus 1 into y is equal to 0 implies that either lambda is equal to 1 or y is equal to 0. Therefore, the only eigenvalue of L is lambda is equal to 1. But if lambda is equal to 1, then y is equal to 1 minus 1 into x, which is equal to 0. Therefore, the set of all x, y in C2 such that L of x, y is equal to x, y is equal to the set of all x, 0 such that x belongs to C, which is a one-dimensional vector space. Now notice that if at all we can find a basis with respect to which L has a matrix that is diagonal, then there exists two linearly independent vectors on which L acts as scaling. But here the only eigenvalue is 1 and the eigenspace for 1 is one-dimensional. So two such vectors cannot exist and therefore we cannot find such a basis.